you know, in full view here. It can be put in the corner if you don't like it. John Walker's not coming in? That's it. You see, so it's up to us, is it? Okay. Shall I just start? Hello everybody, it's very nice of you to come and listen to me talking a bit about the nature and the history of cybernetics, and I believe that none of you know what it is, and that's good because we can start from scratch. I, as you may know, however, have been mixed up with cybernetics from the word go, so I have a huge number of recollections, reminiscences, and so on, and probably a huge number of gaps as well that I don't know anything about. So you may wonder why I appear here with no notes and diagrams or anything. But if you think about it, I mean, this is a matter of fact rather a good cybernetic point, as you may come to appreciate later. I don't know how to do that, how to come with notes and give you a formal presentation, because if I once got into that mode, I would find I was writing a 2-3 volume history of the subject, and you know, I don't want to do that. I'm not the least bit interested in doing that. So I have to rely on extempore, on memory, and I've deliberately not thought much about it. I try to put myself in a frame of mind where you few guys have come together and say, hey, Stafford, what the hell is all this about? What is cybernetics? Mm-hmm. And as I came here at the weekend from Canada, some friends gave me a birthday party, and one of the presents I received was this, and I thought it was very apropos. You can't see it. And it says, when your memory goes, you can forget it. Well, this is how I'm standing here, sitting here. So we'll hope that the right memories come. And very relevant to that, the first story I want to tell you is about the only person I've ever had that I could have called a mentor. His name was Warren McCulloch. He was one of the founders of cybernetics, and I was very devoted to him. A most extraordinary man, a physician, a psychiatrist, a poet, a blacksmith. He was all manner of things. He retired as professor of psychiatry from Illinois one Friday night, took his gold watch, and everybody said, strange, because this guy's a living dynamo, why is he retiring? And he opened up shop on the Monday morning in MIT as professor of electronics. So this is the kind of man we're dealing with. And I tell you all this straight away because it's always been an ideal of mine to be interdisciplinary. And cybernetics is outstandingly an interdisciplinary subject. And I think people will tell younger people of your age that it's impossible to know more than accounting or whatever it is you happen to be doing, and you better shut up on everything else. And I want to tell you that this is awful and wicked. You've got all sorts of neurons in your skull you never even used yet, and if you want to know something, go and find out about it. And then if you can start putting various things together that normally exist in compartments, then you will become a holist. And that's what I personally set out to become. And then I stumbled, as you will hear, on cybernetics, and I found that I'd got a science of holism to hand. And that's the first thing to say about cybernetics. Now, I was telling you about Warren. He was a very, very famous man, and I was very privileged to know him. And at the time I'm talking about, I was Director of Management Science in the steel industry. And the date is second half of the 50s. And I used to go and see Warren in the States, and he would stay at my house in Sheffield when he was in England. And I used to bore my immediate management team. I had 5 managers in my group by telling them all these stories about what Warren had said about this, that, and the other, and they got very bored with this. And they said, I don't believe this. One of them said, I don't believe this fellow exists. Why don't you produce him? You see, so I said to Warren, look, will you come and have lunch in my management dining room, you see? So he did. And after the coffee cups had been cleared away and we got to know each other a bit, I said, well, Warren, say something to us, start a discussion going. He said, well, there were 2 monks called Friar Bungay and Friar Bacon who built a brass head. Now, I don't know if you people know about brass heads, do you? In the Middle Ages, people used to build brass heads with a view to using alchemical methods, getting them to speak. And so it was a popular pastime, apparently. I mean, it's historically true. So Warren's story concerned these 2 monks who built a brass head, and he didn't say anything, and they're getting tired. So they asked their apprentice, and they said, we are going to sleep. If this head says anything, wake us up instantly. So nothing happened, but in the morning they came in and the head had exploded. And they said, what the hell happened? And the apprentice said, the head said, time was. Well, we know that, so I didn't think it was worth waking you up. And then the head said, time will be. And we knew that as well, so I didn't wake you up. And then it said, time is, and exploded. Sorry. So Warren told this story. And then in Bart, and I wish I could do this part for you, but I can't, on an account of the nature of time and perception and epistemology, which is the science of how we know things, and he embroidered a thing which went on for a couple of hours. It's just magical. Now, at the end of that, one of my team, everybody had joined in except one man who was an ex-professor of philosophy that I had acquired from Manchester University, a very well-known man. And he said nothing. So in the end, I said, Peter, you haven't said anything. I mean, why not? But say something. And he said, well, I'm very sorry, but I'm not in sympathy with this whole business. So I said, well, you might as well tell us why not. And he said, well, I happen to be an expert, as I think you know, Stafford, on medieval philosophy. And these 2 friars, to which our distinguished guest has referred, lived 187 years apart from each other. Now, what are you to make of that? I ask you to think about it, you see, because here we had this beautiful disquisition introduced by this story about the head. And here's this guy absolutely resisting because he has caught the man out in a fallacy. Now, this is totally contrary to my way of looking at the world. I mean, that fellow is. I'm with Warren. And I've told you this because I want to loosen you up. I'm not trying to sit here and give you the kind of reading from the 2-3 volume story of cybernetics that I'm not going to write. I'm trying to convey something to you, okay? Just as Warren was trying to convey something. And I hope you can accept it in that spirit. And if it turns out that I'm talking about people talking together and they've missed each other by 100 years or so, I don't expect you to get upset about it, because that's not the point, you see. One of the problems about universities is that you're supposed to be scholarly, and if you're caught out in that kind of error, you lose all your credibility. Which, of course, if you pursue that way of thinking, turns a university into a kind of supermarket of facts. We're not here to do that. We're here to think and to wonder about things. So, with that explanation, I want to take you to the actual birthplace of cybernetics, because the subject has a name, and of course it's always existed like everything else. I suppose there was biology before anybody called it biology. And we know when this started, and it started in the early 40s, and it started in Mexico City, of all places. And the reason for that was that a lot of the world's greatest scientists were working on wartime projects. Note the date, you see, early 40s. And they were sort of evacuated to a neutral country, to Mexico City, to work in peace. And they were working at the Clinic of Neurophysiology, headed by probably the world's leading brain expert at the time, was a man called Rosenbluth, Arturo Rosenbluth, who had this place, and he became the host of this gang of folk. Outstandingly among the gang of folk was Norbert Wiener. Have any of you heard of him? Well, he is known as the father of cybernetics, so that's why I have to introduce him straight away. But like everybody else present there, he was a leading authority in his own field, in his own right. And nobody had invented cybernetics yet as a word, see? So he was a world-ranking mathematician. Any mathematicians around the room? Well, maybe you've heard of harmonic analysis at any rate. We're not going to have lectures on harmonic analysis, but this was Norbert's field, and he was a very famous mathematician. Rosenbluth I've already introduced, and he had experts in practically every subject there is. Now, I said at the beginning that this is an interdisciplinary subject. This is about holism. So now you can begin to see from this story why it was that the whole thing was spawned in the ambience of a gang of world authorities in all sorts of fields. And they formed a sort of club at night. Now, Rosenbluth was working, I'm sad to say, on nerve gases and things of that kind, because he was the neurophysiologist. Wiener, the mathematician, was working on gun sights, how you track a moving target without overshooting. Obviously, if you're going to shoot an aeroplane, you have to fire in front of him, which means you have to be able to, this is pre-computers as we know them, you have to be able to compute where the aircraft is going before you pull the switch. And all these things were going on. So I was saying they formed a club to meet at night. None of them had their spouses with them. They had distinguished visitors who used to come and stay to see how everybody was getting on. And among them, notably, all these people became my friends. I was a very lucky young fellow, I can tell you. But I'll explain why that was later. A woman who became a very close friend of mine, Margaret Mead, and I'm sure you've heard of her, the anthropologist. Sex life and so on, of the native peoples. So all these people were coming and going. Ross Ashby, distinguished British psychiatrist, used to go there. So all these people meeting and talking. So they said, well, what should we talk about? Because they realized, it was a hell of a strange company, very distinguished company. What should they do? So somebody said, look, and this bears on what I began with about universities. We have divided up the world into compartments, and this is called physics, and this is called chemistry, and so on. How do we know that God knows the difference between physics and chemistry, just because the university says so? Or biology, for that matter. Now, I rejoice in a name which is about the only product that has physics, chemistry, and biology all working together, namely beer, that some of you were drinking at lunchtime. Most things are kept in compartments. If you think about it, we don't use products that involve many sciences. That's strange, but the reason is obvious, because they belong in faculties. And the faculties do things in universities, and it gets projected through professional societies, research institutes, government grants and whatnot, and you end up with the product being in a compartment. Very extraordinary. So they were sort of aware of this, and they said, can we think of a subject which has perhaps got lost because it never had a label? And they came up with the topic of control. Now, just please help me with this. Suppose you were the world's leading astrophysicist. What would control mean to you? Someone tell me. Now, you know what's going on in the universe. Ever heard of Newton? Come on, what would you think of as control if you were an astrophysicist?
Gravity.
Yes, it's indeed. Gravity, the equations of motion, the elliptical orbits of the planets, all this stuff would be your notion of control. And you would see the sources of control as being the laws of motion, law of gravity, all those things, Newton's second law and all of that. And if you were sophisticated, you would soup it up with a bit of relativity and quantum mechanics, and this would be your notion of control. But if you were Rosenbluth and the world's leading expert on the brain, come on, what do you think control is now? I mean, you get up, why don't you fall down? That's control. So something's going on in your central nervous system which causes you to be in control, as we say. Unless you're bananas, but most of us, most of the time, are in control. So what I'm trying to say is, you pick any subject, you were going to have a totally different, mind you, conception of what we mean by being in control. And they thought that this was pretty damned interesting. And they decided to talk about control from each person's standpoint. And they took a night each. That's how it started, to say, well, what I think about control because I'm an astrophysicist, and what I think because I'm a neurophysiologist. What would a politician say about control? What does an economist say about control? Are you getting the feel of what I'm trying to say here? That everybody's concept is quite different, and yet we have a concept of being in control, which means something like, well, everything isn't absolutely going crazy. It's coherent in some sense in all these fields. So the question arises, you see, whether there are some principles that are around here somewhere by which things remain in control or are regulated or whatever. Because you don't have to think long about this before you realize that the word control, which I think conjures up pictures of people pulling levers and switching switches and controlling, and if you go into the political field, you tend to think of fascists with guns, and you do that or you're shot kind of stuff. But you don't have to think about it long to realize that the notion of control as exhibited in that way is really quite trivial compared with what happens in nature, with the seasons succeeding each other, with preys and predators bearing on each other. All of these are regulatory things. I mean, why aren't we up to hearing caterpillars? The cabbage aphis weighs how much? I don't know. A little tiny bit of a gram. Now, someone calculated, you take one cabbage aphis. These guys are parthenogenetic. They don't have to have two to breed, which must be a very boring life for a cabbage aphis. If you took a single cabbage aphis at the start of the season with unlimited supplies of cabbage, there would be about 3 billion tons of aphides by the end of the season. Now, so why aren't we up to here in aphides, caterpillars or anything else? You know the answer. Some guy comes along and eats these fellas. Now, if you had to design a system, some of you are into the business of managerial design and so on, you had to design a system which had that amount of freedom of propagation, and you were told to invent a control system, it seems to me either you would not succeed and we would be up to here in Aphides, or you would succeed all too well and you'd make the poor little devils extinct. The idea that you could keep them at just the level you need to fill an ecological niche is daunting, isn't it? So you see, once you start thinking about this, you say, hey, just a minute, this is a very, very extraordinary topic. So that's what these guys started to do. And they began by giving themselves each a night to say, well, in anthropology, control means this to me. And you can see what that is. In anthropology, it's all about the balance of tribes and of foodstuffs and wealth, however defined. You see, everywhere you look, you see the concept, and it means something different. Well, to cut that story short, what they discovered was that it took them more than a year to interpret to each other what they meant, because nobody knew the words. You see, the physicist launched in and said, well, you know, this is a pi meson, and this obviously all this. They said, just a minute, what's a pi meson, you see? So everybody has their own vocabularies and their own paradigms, to use the word, of what constitutes control. And it really took them all this time to sort this out. And gradually they came to the belief that they had stumbled on a new science, that there were principles of control which seemed to apply everywhere. Now that, if true, you see, becomes a very astonishing and exciting point, doesn't it? Excuse me, I'm very dry. Now, I want to tell you a story about what happened in the middle of this process, which I believe, and I warn you in advance, should give you a shiver down the spine, a frisson. So if it doesn't, go home. I don't want to bore you any longer, so there's a threat. Here is Norbert Wiener, the mathematician, and this story is true. I heard it from all the people who were there separately. So I've got really veridical statements on my plate here. Norbert's sitting there reading in the common room in this establishment in Mexico. And a little guy comes in and said, got a minute, Norbert? Yeah, I have, and this is an electronic engineer talking. And he said, I have come up with an idea about how to make blind people read with their ears. Oh, charming. That sounds good. Now, after all, Braille, very expensive. You have to translate everything and then teach people to read Braille. If you could read with your ears, obviously that would cut out a lot of processing, wouldn't it? So I'm all ears, says we know. God, he couldn't have said that. I'm sorry. He said, tell me. So this chap then drew, and I've got this diagram somewhere, but it doesn't, again, it doesn't have to be accurate, excuse me. He drew on a piece of paper a sort of stave like that, and he said, look, this is time going in this direction. So he said, here's a page of print, and I propose to scan it through time with 3 photoelectric cells. Now, this one will sound a note, and so will this, and so will this, and they'll be members of a chord. So, if we've got an eye in the print, this thing will intercept, this P cell will not be triggered. These two will be triggered, and it'll go boing, these 2 notes. If we get a T, it'll trigger all 3 notes. Sorry, an L will trigger all 3 notes. A T will trigger all 3 notes, and this one will be sustained. So you got boing, So gradually you could train the ear, he says, to understand what this means in terms of words. And after all, if you think about it, a word like the, T-H-E, would have a complex little gestalt, wouldn't it? It would be a pattern with the boom, ding, boom, funk, and that you'd say, oh, that's the. So, fair enough. Now, how would you build this machine? So he's starting to look at this. So he says, well, we need these photoelectric cells, and we need an array of them which are differentiated in time, this being time. So we've got these things happening like that, and returning. So we've got to build a special purpose computer. Don't forget there weren't any computers. This is thinking of, as an electronic engineer, about the machine you could build. So we've got this kind of array, and then obviously there's got to be a connection between this and that and that. And so you get a scribbled diagram that he was talking about to Wiener, and it looked something like that. As I say, I've seen it, and I could send it to you if you really wanted it. But that's good enough. That's the sort of diagram. It wasn't an electrical circuit, you notice. It was a schematic. A schematic diagram explaining how he thought this machine might work. And Wiener encouraged him, and they agreed it was an idea worth pursuing, and the electronics man went to bed, took his whiskey and left. So Wiener resumed his book. In came Rosenbluth, whom I already told you was the director of this institute and the world's leading authority on the brain, neurophysiologist, went to look for a magazine on the table, found this line there, and he said, you ready for this? He said, Norbert, who has been trying to draw a diagram of the fourth visual layer of the cortex? Do you get it? And I've told this story a million times. It still gives me a shiver. Because, wow, what's going on? Now, Wiener was thoroughly excited about this, and he called a meeting of the club the next night, and he explained that this had happened. And he said, well, I'm a mathematician, and after all, how could we quantify this diagram? Supposing the visual cortex does work like this, how can we quantify it? So he said, I wonder if at this level you've got inputs coming up through synapses and so on in the nervous system. Does anybody by any chance know the rate at which these pulses are going to arrive in this network? So somebody says, well, yes, of course, my students have done 17 PhD theses on this, and I can tell you it's this rate. So gradually, Wiener was able, standing at the blackboard, to quantify this diagram. And then he took another board and he said, okay, this thing is going to have a scanning rhythm. Because if you move a thing across a page of print, then it's going to establish a rhythm with which all these sounds are produced, obviously. I forgot to say, by the way, that I should have said this, that the reason for all these interconnections is that, I'm so sorry, I missed this story out to this extent, that if you've got a page of print, if it's specially produced, then you can align your photocells with this size of type. But if it isn't, the machine has got to have a built-in ability to move its photocells to align with the size of type. Otherwise, you'd have to print every book specially, and you might as well print it in Braille. You know? So this is why all this interconnection, because of trying to perceive where you are with a text. So I'm going back to all of that, where Wiener is quantifying this and saying, well, any such machine, whether it's a thing invented here or whether it's a brain, would develop a scanning rhythm, and I propose to calculate what this rhythm is. Now, so this is going to be cycles a second. Any guesses? How many cycles a second did he compute? Answer, 10. What's 10 cycles a second? Anybody know? the alpha rhythm of the brain, the resting state of the brain. So another frisson, anybody? I mean, not only have we got this idea now, but we've quantified it, and by golly, it works, you see. Now, this kind of thing was what set everybody alight, and everybody saying, by God, we're onto something, and there is a subject here, there is a connection. Are you clear with me so far? So they said, well, what is it? It's a science of control of some kind. But after all, let's remember that we've already said that control is a very trivial idea, to think that control means beating people over the head or pulling levers. It's much more subtle than that. So what is this a science of, if we don't want to use the word control? Oh, this is hard work here. Golly. Sorry, it has to be done. I'm on overtime. I think this cloth ought to be wetter. If someone's listening with a wet cloth, please bring it in. Golly. So, the reason I wanted that cleared was, does anybody know Greek? You must know something here. You deny knowing mathematics. Does anybody see this word? That is Kubernetes, from which we get cybernetics. And it is the Greek word for a steersman. Now, this is a bit more sophisticated than beating people over the head. If any of you have ever read Homer, they were full of long ships, and you imagine the guy at the back of a long ship with a tiller, and he's trying to get over there, and there's a light burning, a lighthouse. He had those. So he's got to get there, and he's got the wind and the sea and the rain and everything bashing him. He hasn't got a computer. So how is he going to get through this mass of variables, we would call them, that we can't measure and can't compute because we don't know the equations? What he does is he fixes his eye on the light and juggles, and he gets there without knowing why, you see, but he's steered there. So Wiener and the guys said, this is a nice image. It's not a nice word. I've cursed it ever since. People say, cybernetics, what's that? I had what do you call it, an immigration officer in New York said to me, I used to have cybernetician in my passport till I realized it was too much trouble. I now have professor. Everybody knows that. You've got a beard, okay. So this immigration officer said to me, cybernetician, I know what that is. You freeze dead people. Have you heard of cryogenics? So, confusion. So I don't like the word. It's been a nuisance. On the other hand, etymologically, as I'm trying to show you, it's more or less perfect. Because control in a regulatory sense about how you are steering isn't about bullying anybody, isn't about knowing the machinery of doing it even. You know? It is a question of having something that you want to achieve and finding ways that work of achieving it. Manipulating a system, if you will, so that it produces the desired result. Now, that is a very nice idea I'm suggesting to you. And if we transliterate the Greek into Latin, the U, this part, that's a rho, so that's an R, that's an N. And in Latin, we get this ending, and the K gets harder and becomes a G. So in Latin, we get gubernator, and of course, that goes straight into English as governor. Now, thank you. The interesting thing about these words, we've got now to the English word governor. Now, what does that mean? You think, supposing you were governor of a prison. Now, you've got some variables under your control called convicts. So you go off and you have dinner with the mayor, because you're the governor of the prison, and all the elite are at this dinner, and in the middle of dinner someone comes with a note saying all these guys have escaped because they've dug a tunnel, and while you were sitting here eating, they've gone. And we've set the dogs out across the moor after them, but we can't say what's going to happen. So you see, you've not got your variables under control, this kind of governor. Now, here is another kind of governor. Do you recognize this drawing? Does that mean anything to you? This is the Watt steam governor that I've drawn a caricature of. So you've got a shaft which is whizzing round like that. And if it goes too fast, centrifugal force drives these two weights out, which pulls this sleeve up, which cuts off the fuel supply. That's how that works, invented by James Watt. I think one of the earliest cybernetic inventions, because what this is doing, you'll notice, is keeping a runaway variable under control, like the convicts, but it brings it back into the control in the very process of it going out of control. It uses the fact of it's going out of control to bring it back into control, and you can be going having another beer in the bistro, and it will work. Whereas you can't go and have dinner with the mayor and let your convicts escape. Now, I believe that we have here a very vital management principle that you would like if you were the manager of something, that if something's going wrong, the fact that it is going wrong would bring it back into control, and you could spend your days on the golf course. Instead of sitting around hoping against hope that you will spot the thing going wrong and beat it over the head before it's gone too far and you're all in jail. So this is where the management end comes in. Now, none of these original guys was in management. And I think I have to bring myself in here at some point. I was thinking these kinds of thought when Wiener's first book appeared. It was published in 1958. It's almost unreadable. It's a great joy. He wrote it in 3 weeks because he had pressing tax demands. And he thought, well, might as well write a book about cybernetics, you see. And it's full of quadruple integrals. You said you didn't know any mathematics, but that's this F sign, that terribly complicated stuff. And he's got little rhymes in German in there, and huge philosophical disquisitions and loads of stuff of all kinds. It's very hard to read. But because I had always trained myself to be interdisciplinary, this book set me absolutely on fire. I read it in 1960, I know that. And I wrote to Wiener and said, I think I'm a cybernetician, you see. So that's how the lucky young man got in with a gang of people old enough to be his father, you see. And I met Wiener and I met all the others, and Warren became my mentor, as I've already said. So that brings me into the picture. Now, look at the background here. Think of the time we're talking about. I've now got to 1960. What was happening in the 50s? Well, the people who were involved in all this persuaded the Josiah Macy Jr. Foundation to fund an annual conference. And those books are more precious than gold. They're proceedings of the annual conference on cybernetics. So I managed to get hold of all those as soon as I discovered this, and you can't get them now at all. They're collector's items, and I'm pleased to tell you that my own collection of those is right here in Liverpool, because, as you may have read, this college has acquired all my books. So there you go. So those conferences began to report what people were doing with these ideas, and other guys got sucked into to the proceedings, as I did myself in 1960. And so the whole movement was born. But I was asking you to contemplate what else was happening at that time. Notably, you see, computers were being invented. And of course that bears very heavily on this, because they became an instrument for pursuing this kind of thinking. And that has ended up with artificial intelligence and God knows what else besides, after all, as you well know. So here was I, and I'm gradually trying to weave my own story in here. Here was I in the 50s, not knowing about Wiener and the word cybernetics, messing about with the original computers. We had the first stored memory computer that ever worked. Where was it?
Manchester University.
That's right. See, all Americans think it was in America, and it wasn't. so there. It was Manchester, you're quite right. And there's a plaque on the wall to commemorate it. So I used to go from Sheffield, where, as I think I mentioned, I was head of management science in steel, and I used to go to Manchester to look how they were getting on, and then Cambridge had EDSAC, and we used to take that in, and the National Physical Laboratory at Teddington had a thing called ACE, which then became JUICE, and all those. And at that time, it wasn't at all clear whether the digital or analog versions of computing was going to triumph. And the Royal Aircraft Establishment at Farnborough had an analog computer which filled six semi-detached houses, that is, say, 3 houses, 6 of them, 3 buildings. And there wasn't, towards the end of that, there wasn't anybody who knew how it was programmed. So many people had worked on it. It was a real lash-up. And so were digital computers. You open the back of a digital computer, it was a massive valves. We hadn't got a transistor, don't forget. A massive valves connected by something that looked like a madman's knitting, because everything was taken direct with a wire and soldered on. So you got all this knitting, and if anything went wrong, boy, oh boy, you were 3 days trying to find out what the fault was. And since if you've got an assembly of several thousand valves, cold tubes, whatever you call them these days, one blows about every 3 seconds. You see, whoa, it was hell in there, I tell you. So I used to go on this round of these computers and wonder about how to advance, because I was putting in automated systems in the steelworks of a very, very primitive kind. As I said, we had no transistors. The first bunch of transistors I got my hands on, I tried to solder together into something, and the heat of the soldering iron, as soon as it approached one of those 3 prongs, the thing blew. Didn't like the heat. So it was very obscure whether the transistor would ever work, and just think what's happened in computers since. So this is an aspect of cybernetics, and a lot of people think that cybernetics is about computing. Well, it's obvious to you, I'm sure by now, that if you're going to talk about control and regulation, then manifestly you're going to have to talk about computing, simulation, all these kinds of things. And if we'd never had computers, we'd have had to do it some other way. But we have got computers, and we've gone down that route. But equally obviously, from what I've said so far even, I'm sure you can see that to mistake the tools of the trade, namely computers and theories of management information systems, and all of that, to mistake that for cybernetics itself is absurd. It's like mistaking the kitchen for the dish you eat at the end. The culinary insight is not in the utensils. So, this is how the whole thing began to burgeon. Now, I started in the States. I want to switch to England. Well, I just did with the computing area. But as far as cybernetics itself went, I've talked a bit about Wiener, and I now want to talk a bit about Ashby. because Ross Ashby, who was head of an asylum, of all things, in Bristol, I'm just trying to remember the name of it, it won't come. Never mind. He was a psychiatrist, a man who thought very deeply about the brain, and who formulated a set of theories about how the brain actually works. And he wrote a book called Design for a Brain, which looks at very fundamental mechanisms that must be satisfied if the brain is going to work. And outstandingly, the notion is homeostasis. Now, I don't know if you know that word. I expect you've heard the word, but what sort of insight do you have into the notion of homeostasis? Well, homeostasis is that natural system of control, if you will, which keeps variables within physiological limits. The most obvious example is your own temperature. 98.4 and all that jazz. No surgeon has found a thermometer, a feedback system, a relay inside you set for 98.4, and yet here you are, and you can go on to a melting shop stage, steel melting at 1450 degrees, and then straight out of there into a butcher's freezer, and somehow your temperature adjusts. Now, there is a very cybernetic truth. How does it work? So homeostasis is how it works, and Ashby was the man who penetrated that mechanism. So Design for a Brain became very important. So I extended my tours of computers to include Bristol. You see, it started making friends with Ashby. Now, I don't know what's up with Bristol. Some of you come from Bristol, but the air must be good. Because also in Bristol we had Grey Walter, who was the head of the Burden Neurophysiological Institute in Bristol, who was a world authority on electroencephalography, the EEG, the brain rhythms and all that. So he had theories about how the brain worked. And he started building machines that illustrated these principles. Now, I'm going to get bogged down if I'm not careful, because Ashby invented a homeostat which was made of magnets and coloured lights to study the principles of homeostasis. And Gray invented a tortoise to examine how other physiological principles worked. And down the road in the university, there was a psychologist called Frank George, who was also trying a behavioural approach to how behaviour is governed. And his department was full of monkeys, this kind of psychological approach. And Frank replaced the monkeys with electronics and fell foul of his professor, who was a monkey expert psychologist. So you have all these trends going on, and high excitement and a lot of tension and drama and so forth. So gradually this thing came together, and I haven't yet given you Wiener's definition of cybernetics, but against all this background, I hope you'll appreciate it better. When he wrote this book, 1958, as I told you, he defined cybernetics like this. He said it is the science of control and communication in the animal and the machine. Now, nobody understood that, and I don't suppose you do either, although I've told you enough. If you went away with a wet towel around your head and thought about it, you may get some real insights from that definition. But let me help you with it. Take the first part, control and communication. Now, why communication? Well, it's become very, very clear in these early days, during all this talk and building machines and so forth, that regulatory being in control is absolutely dependent on the communication and the flow of information, that means, by which the thing is supposed to be controlled. Never more true than in the central nervous system, quite obviously, that nothing happens unless pulses are flowing through the nerves. And it's the same in a machine as well. And so ho-ho, control and communication becomes a central concept to cybernetics, and that's what Wiener was drawing attention to with his definition. As to in the animal and the machine, now we're really talking dangerous stuff here. Because if you think about university and the way knowledge has been organised, it has made a tremendous division between animate and inanimate, has it not? You know, physics and chemistry over here, the physical sciences, and over here the biological sciences, and latterly the social sciences. And there's a huge divide here, and you're not supposed to be able to cross it at all. Whereas what the cyberneticians were discovering was that there are indeed principles of control, and I've already mentioned homeostasis. I shall mention several more as we proceed. There are principles of control which apply whether you're talking about brains or computers, or for that matter economies, or political systems, or anything else. So what these things have in common is that you've got a very large probabilistic system which is whizzing around and somehow is achieving the in-control notion because of the way it's all internally organised, and not because somebody's come along with a hammer or a machine gun or a set of levers. Now, if you just apply that thought just even for a second to what is going on in economics these days, with economists all at each other's throat about how you control the economy, you know? And you can begin to see that they can't even begin on it because they've got simplistic theories which are like hammers and levers. They say control the money supply, that's it. Like hell it is, as we've discovered. It doesn't work. The controls are implicit. So the nearest they've got to a cybernetic statement is the notion of market forces, which is a pretense at seeing what is implicit. But that's only a fraction of it. And that's why, in my opinion, the pursuit of the market force economy is so devastatingly wrong. It's right to the extent that it's better than saying control the money supply. It's looking at a self-generating piece of machinery. But it's not an adequate explanation, as we keep on finding out, because nothing works. So I'm trying to sell you the proposition that there are cybernetic principles which apply absolutely everywhere, and you can flit from economics to the brain to the computer and so forth, and this is what the subject does, and it's extremely rewarding for that reason. Now the next thing we have to consider there is that because it flits around in this way, people are fond of saying, well, this is simply analogies. This is very unscientific. Stafford, go home. It won't do. So very early on, I found myself, I was originally, as a boy, I was a mathematician, but as a student at university level, I was a philosopher, and I got very, very interested in epistemology. I read philosophy and psychology, and the philosophy pushed me down the route of theoretical logic, which brought me back to mathematics in a kind of a loop, and the psychology pushed me into statistics, mathematical statistics, as the only way you can grapple with the quantification of chancy systems, and into neurophysiology, because it seemed to me that talking about the brain from the outside without knowing anything about how it works is kind of wild. So all of those things come together in cybernetics, and it was pure joy to me to be in that and to look at all these machines and to build an epistemology that would account for this. And I think the next thing I would like to do is show you what that theory is about, because it really is damaging scientifically if your response, for instance, to all this yarn would be to say, well, you know, there are obviously analogies, so Stafford says, and they're fairly obvious once they're pointed out, between machines and brains and economies, but really this has got to be suspect, it's not scientific, it's, you know, and indeed we've encountered a lot of that opposition. One of the very big strengths was from the start that the leaders in this field had nothing to prove. They were already well famous in their own subject, so they didn't, you know, you couldn't sit there and accuse a Wiener of sort of being a Scientologist or something, making it up as he went along. So I published this theory that I'm going to sketch in for you now in a book called Decision and Control, which was published in 1966 and is still in print, I'm proud to declare. And the theory goes like this. It says, well, here are the two things that we're talking about, like a brain and a computer, or a system of preys and predators and a mathematical theorem, you know, things apparently dissimilar, to which we are drawing attention and we are saying, hey, just a minute about, because this is behaving like that. Now, it is fair to call that, when we start, an analogy. And if that's all it was, it wouldn't be very scientific. So I argue that what you do then is you try and formalize these two things. You come down here and you look again at the comparison of two formalizations. Now, ideally, I suppose, those formalizations would both be in mathematical terms. But even if you can't make that grade, you're being far more rigorous than this original metaphorical impression. You're trying to formulate the thing rigorously. Now, people like John Stuart Mill looked at inductive logic in this light and formulated principles in the 19th century as to how one might have a rigorous analogy. So I wish I hadn't written that. Get rid of it. Let us call this level purely metaphor. With you, my love is like a red, red rose kind of stuff. You see, now I prove it. So this becomes formal analogy at the point where you can make this rigorous, and Mill's methods and so on are relevant. If you come down still further, let's say now that we have got sets of mathematical equations and we are looking at the relationship between them, then this is a homomorph. Again, I'm sorry, you said you don't want mathematical terms, but that is the word for a mapping of one thing onto another which isn't exact, but which is nonetheless telling us something. For example, if I have a model of a building, and you say, oh, I know what that is St. Paul's Cathedral or Tower Bridge or something, you wouldn't confuse them, although it's only a model. And if you come along, I've cast you in the role of carping critic, and say, hey, this hasn't got the right number of bricks in, you say, I come off it, you know, that's not relevant. So these two things are homomorphic. The actual St. Paul's Cathedral and the model are what are known in mathematics quite graphically, I think quite easily understood, as many-one mappings. So you've got lots of bricks being represented by one brick. And this is the kind of expectation you have at this epistemological level in trying to understand what that relationship means, if anything. It may not mean anything, it may just remain a metaphor. And then you come down, and this is scientific progress, because these two things now, if you're lucky, become homomorphic. I'm sorry, I said homomorphic already, the many-one mapping. These things now become isomorphic. Iso, as you know, with isobars and all that stuff in meteorology. Iso means the same. So that mapping is identical. Now, surely you might agree that if you start with a metaphor and can press down to the point where the same equation works in both things, then you've got the scientific principle on your hands. Now, the most obvious example of this in cybernetics was the thing that they first stumbled on in Mexico City. And it is the principle of feedback, and especially the principle of error-controlled negative feedback. Now, you've all heard the term feedback, and mostly it's terribly abused. People say, give me some feedback on my lecture, by which that means, was it all right? Well, this is a terrible loss of meaning, because a feedback takes the output of the system and compares it with something, such as what we would like the system to be producing, and feeds back an error signal on which the machine can operate. Now, this science is particular to servo mechanics. So if we were looking at this as servo engineers, we would say, well, we've got this process going on like this. To take the simplest case, this is the output of the system. We've got something going in, and this is coming out. And we are measuring it, and it's fluctuating, okay? Now, this should be 30, let's say, because we've set that as our target. And it keeps coming out as 29, 28, 27. Oh, you say that's too low, right? And you measure that, and you feed back here into the system, and you say, I'm taking the very simplest case. Let's suppose you're more or less averaging 27, then the error signal says, put another 3 in, and lift this, and now you'll be nearer 30. So that is an error-controlled negative feedback, because it's measuring the error from some standard and pushing it back and correcting it. Now, you can have positive feedbacks. For instance, a servo-assisted brake is a positive feedback. By pressing on the brake, you get more brake, not less. And those principles, you see, you find absolutely everywhere. And economics is littered with that, which most economists don't know. They don't recognize because they're not thinking in these terms. So obviously, once you think about it, isn't it obvious that things happen in the economy which tend to reinforce or tend to check? So various people have tried to rewrite economics in cybernetic terms, and of course the economists don't like that happening to them, and there's uproar. But that's what cybernetics is about. So let's talk a little more about this feedback principle, because I want to show you how enormously relevant it can be, and we're in a management school here, so I want to make it clear. If you just took the signal and kept feeding it back as simply as I have explained there, what do you think would happen? This goes down to 29, you say put a 1 in it. It then goes to 31, you say take 1 off. What do you think is going to happen? No response.
It's going to hover around the 30.
You're right, it's going to do worse than hover. It's going to go into an uncontrolled oscillation. It's going to get worse and worse and worse. And the more you try and correct it, you overcorrect it, and woof, the thing will blow up. And what happens is this output is wobbling, and it wobbles like that, and bang. And that's an uncontrolled oscillation. So to get over that, what you do is you put a feedback function in here, which is cleverer than that, which collects the information coming out of here and effectively damps it. So instead of leaping in and saying, don't do that, you see, it says, well, just a minute, there's a tendency towards being too low, so let's gently up it and see where the equilibrium point will come. So that's what you try and do, and you can see that in your own physiology if you think about it. If you corrected every movement you make without this kind of box in there, you would become spastic. Because you try and seize this glass, you say, my hand isn't going in the right direction, before you know what you're doing this. And that is indeed a condition. It's called ataxia. And it's a fault in the cerebellum of the brain that is supposed to do this damping function and doesn't. Because you're ill. You're pathological about that. So what you have to do if you're designing this kind of system is put this in. Now it's a pity there isn't even one mathematician here, because in order to specify that box, you will need a set of equations. Obviously, if you're building a system. Now, the key equation that's going to do that in any system that you are actually studying is called the characteristic equation of the system. Very non-mathematical term, you can understand that. Well, if you analyze the characteristic equation, and this is where I'm fishing for a way of expressing a mathematical thought. It has roots. Now, you all know what a square root is, such as 4 being the square root of 16. Well, characteristic equations have roots as well. And they are of two major kinds. I'm wrestling here with a notion. All I can do really is blurt it out. We speak of large negative real parts to a root or not. Now, a system with large negative real parts is absolutely characteristic of a social system. So when you apply this kind of servo-mechanical thinking, using my epistemology to a social phenomenon, you must expect that this thing will have large negative real parts. Now, why am I telling you this? I mean, it gets very, very interesting, or I wouldn't be bothering you with the terminology at all. If you have high gain on the system, where the feedback function has large negative real parts, what happens is that the feedback takes over from the input. Now that is an extraordinary fact, but it is a fact of servo-mechanical engineering. And I already told you this applies in social systems, which I could demonstrate, but you would need the mathematics to follow it. Now, look at the consequences of that. If you just accept what I'm saying, please do for the moment. You look at the role of the media in the life we lead, in understanding politics, in understanding the world situation, in understanding economics, etc., etc. Now, in fact, the media are playing a feedback role. They're trying to correct your understanding, aren't they? Your understanding is thus and thus. Along comes a television program which says, you are misreading this, in effect. We will tell you. Now, you think, don't you, that you can accept or reject that message. And you say, well, that was interesting, but I don't believe a word of it, or not. But the problem is, if this cybernetic treatment is correct, this will gradually take over the input. In other words, what you know about the situation will all be coming from the media because you haven't got any other source of information, because this is dominating the circuit. After all, where are you going to get it? Somebody comes home and says, I've just been in China and it's like this, and you say, oh yes. But the next program on China, you see, is going to correct this impression. Fast, probably. Now, I have a paper which I think, if you're interested in this bit of what I'm saying, I think you might well enjoy, called The Will of the People, which I'm sure can be made available to you here. which tries to analyse what happens in a democracy to the will of the people, which gets destroyed by all manner of stuff, which this is a major mechanism. There are many others. So this is my cybernetic address to the problem of how society regulates itself or fails to. And I believe that our societies are in a catastrophic situation right now. Everybody, I say everybody, a lot of people are crowing about the collapse of Soviet communism and not noticing that our own society is following closely behind. We've got a third of our people in Britain and in the States and in Canada. Just an interesting figure. I mean, why do we get these same figures? Because they're a function of a system. We've got a third of the people below the poverty line. Well, that's not very clever. Etc. And you know about the homeless, you know. We get to learn to live with this stuff. And because we get conditioned by this kind of feedback, we don't find it at all surprising, whereas we should be absolutely outraged, I think, about the state of the world. And if you take it at a world level, you've got a third of the world starving. And if you increase starving to include undernourished, it's 2/3 of the world. And here we are saying, oh, well, the hell with Soviet communism, that didn't work. We are the winners. But we couldn't manage a fish and chip shop. That's how it seems to me. Now, the cybernetics of all this is what I've spent my life examining, and those of you who wanted me to tell you over lunch what it was all about, I've got there now, more or less. Hours later, I hope you can get some feeling for what is involved in this, and the high excitement of an approach which is multidisciplinary, which has to accept that if there is evidence from biology, then you've got to transform yourself into a biologist and understand it. And if you need mathematics to do it, you have to learn some mathematics, and so on and so forth. And this is, I assure you, not an impossible task, because you're not going to set yourself up as God Almighty. You're not going to say, I know everything. That's ridiculous. But you can learn what is common to all the disciplines about this topic of regulation, and in particular self-regulation, because we want to design our systems so that they regulate themselves. This is known as autonomy, isn't it? Now, most people believe in autonomy as a political objective, and then it turns out you can't do it. After all, Mrs. Thatcher was always talking about autonomy, and meanwhile grabbing all the power into London and capping rates and doing all the things that stop autonomy from working. It's just a total failure to understand the cybernetics of the situation, assuming there's honesty behind it. If there is, it's a failure to understand the cybernetics. Well, I've got through to a point where I've tried to give you a feel for what this topic's about. We can go into lots more detail, and what I suggest we do, if the timing's about right, gentlemen over there, to stop and get out these lights for a minute, and maybe you talk to me privately and say, well, let's use a second session to do this, that, or the other. Okay? Thank you very much.